What I'm going to do today is just overview the course, try to put everything together, give you a way to put it all into one package so that you can do well on the test. You're probably going to need considerable amount of preparation. So I strongly recommend that you use the open math assignments. You can do the late assignment. And if you have trouble in one, I'll review those every once in a while. Number one, I can insert some notes. Number two, you can email me or put a question in using open math. I'll be monitoring for all that stuff. Okay. I will have some office hours next week, but I can't yet predict what they might be. Depends on a lot of external factors. So I'll email those office hours. I'll post them. So you know when I'm likely to be here. Okay. Glad to give you some help if you need it during that time. So let's just start looking at what we've done in the course. They're foundational functions. Okay. First is exponential. You know how to draw the graph, just the shape of the exponential function. I'm going to do this with no explanation because I've explained it a number of times, so you have access to it. Okay. And we don't want to take time with something you can easily access. There's the exponential shape by construction. And of course, we can sketch a smooth curve. There's a doubling time. Each of these intervals is a doubling time. They're all the same. Look for the function, for the toolkit function is y equals, I'll say for the general function, a times, I'll use t for the variable, a times b to the t. You could also do y equals a times 2 to the kt. And if you understand transformations, you understand that k is a horizontal compression. So if k is a big number, this horizontal scale is compressed, giving you a lesser doubling time. It'll double more quickly if k is bigger because then kt is going to change more quickly. It's an important idea if you can ponder it and get it in your head. And also y equals a times e to the kt, where e equals the limit as n approaches infinity of 1 plus 1 over n to the n. And you don't have to memorize that, although in the past I've always required that. But it's not going to be required that you know how this works. And and left out a 1. It's approximately equal to 2.71828. That's more decimal places than you're ever likely to need. But if you need them, you're probably going to be doing it on a computer calculator, which will have an even more accurate value. Okay. So there's that function. Quadratic function. The shape can again be constructed without reference to any numbers at all. And then this graph can be scaled. Whatever scale its particular transformation. You happen to be using. This is not very well drawn. What's the matter with this? It's really not very well drawn because I don't know where in the head. Oh yeah, you got to skip one. Yeah, I should know that. Anyhow. Here's an approximate graph. It's a little compressed this way. This is not a great graph, but it's serviceable. So there's the shape. Okay, on the exponential, I'll include the formula y equals 2 to the x. That's the toolkit shape. And then if it's stretched, compressed, shifted, whatever, you get any of these forms. Okay, formula for the quadratic function. The toolkit form is y equals x squared. More general form, y equals a times the quantity x minus h squared plus k. Or the general form. Y equals ax squared plus bx plus c. Y equals ax squared plus bx plus c. Now this y equals a times the quantity x minus h squared plus k. It's very straightforward. You vertically stretch by factor a. If a is negative, you reflect it across the x-axis. Then you shift it h units in the x direction, k units in the y direction. You need to know how to do that. You need to be able to do that. Now, in the general form, the ax squared plus bx plus c, the axis of symmetry, is y equals negative b over 2a. So I've shown on the graph, here's y equals negative b over 2a. And it's not y, it's x. X equals negative b over 2a. I'm not sure why I'm writing y. Okay. It's obviously an x value because it's constant as you move in the vertical direction. Okay. X equals negative b over 2a. And you have the vertex. And to get the vertex, you know the x coordinate, it's negative b over 2a. I haven't written it explicitly, but to get the y coordinate, you plug in x equals negative b over 2a. And if you're not sure what that means, then that means you don't recognize it and need to review it, okay? And a lot of times people won't recognize it. It's been a few weeks since we talked about it. Okay, then you have the y-intercept. And it's at y equals c. You plug in x equals 0. You get the y-intercept. As x equals 0, y equals whatever the y-intercept is here. Okay, and that's going to come out c in this form. Then, with these points, you can sketch square in shape, a parabolic shape. Now, again, I always tend to get it too fat on this side, but it's supposed to be symmetric about this line. Okay, so this point here, the y-intercept is this far to the left. Point of the graph should be that far to the right of the line of symmetry. And every point, for whatever y value, should have that characteristic. The x-intercepts occur when y equals 0. So ax squared plus bx plus c equals 0. And x equals negative b plus or minus the square root of b squared minus 4ac, all that divided by 2a. You also notice that the negative b over 2a for your axis of symmetry occurs right here. I've explained at least a couple of times how that works. This square root plus or minus the square root is going to be either this far to the right or this far to the left of negative b over of negative b. Okay, so that the negative b plus or minus b squared over 2ac all divided by 2a is going to be at equal distance to the right or left of the axis of symmetry. Okay, so we know that these 2 points are obtained. You can use the quadratic formula. If you happen to have a function in this form, the algebra is just a little bit simpler. But one way or another, you can find the zeros of any quadratic function you're given and sketch the graph. The function does not have to have real zeros. If I just raise this thing up, say above, so that the vertex is above the x-axis and the graph is opening upward, the graph is not going to pass through the x-axis. So the value of the function is never going to be 0. You're not going to have any y equals 0 points. Okay. And if the graph is inverted, which it would be if a is negative, if the graph is inverted, the vertex might be above the x-axis, in which case you're going to have zeros as it opens downward. Or it might be located completely below the x-axis. Vertex below the x-axis opening downward, it's never going to hit x equals 0. These are the really basic things you need to know. Now, I can't tell you everything, but these are the foundational things. And you apply these ideas to solve the problems. Okay. Now, we also have reciprocal function, and we can sketch its shape. Again, review if you need to review to see the details of the construction, which I don't have time to repeat in this brief review. There's your graph. The toolkit, and of course, this is a shape. Toolkit form is y equals 1 over x. More general forms. Y equals a times 1 over x minus h plus k, which is vertically stretched by factor a. Inverted if a happens to be negative. It's always the way vertical stretch works. And then shifted h units horizontally and k units vertically. So that this point here is the point 0, 0 for the 1 over x function. It's the point hk for a transformed function. So take the risk of labeling this point as 0, 0. The toolkit. HK for general. So the toolkit function is here. General function is here. Important characteristics of the graph. Well, for any graph, and you might well get a problem. You almost certainly will get a problem on the exam or give you some random points. Okay, they're not completely random. You know, one can't be directly above the other or you wouldn't have a function. Fail the vertical line test, which I'm mentioning, but I'm not going to write down. You should know the vertical line test. You should know the definition of a function. One value of y for every value of x. Okay. Then you can have more than one value of x for a given value of y, but just one y for a given x. I'll say it, but I don't want to take time to do it. So if I give you a bunch of random points where your graph looks like this, well, you can sketch a reasonable graph that goes through those points, as long as the graph is smooth and doesn't double back on itself, in which case it wouldn't be a function. Your graph is going to be okay. And then I might give you a scale. I might ask you to put a scale on it. Okay. Go out here halfway between the last 2 points, sketch a vertical line, and call that x equals any number I might want to tell you. Okay, so let's say that x equals 70. Okay. That implies a scale for your entire x-axis. And you can sketch a graph that approximates all the x values. Now, what I would do if x equals 70, I would say, okay, well, if x is 70 here, 64 is going to be pretty close to 70. Now, why is 64 a good choice? Because you can cut it in half as many times as you want without having to do a lot of arithmetic. Okay, it's a power of 2. Okay, it's a 6th power of 2, but you don't need to know that. You just need to know, if you know what the powers of 2 are, you know, just you list some of 2, 4, 8, 16, 32, 64, 128, 256, 512. Oh, why not 1,024? Okay, those are your counting number powers of 2. And then you can go in the other direction. If each of these numbers is half the one before it, then each of these numbers, I'm sorry, if each of these numbers is twice the one before it, then each of these numbers is half the one that follows it. So what number we put here? It's going to be half of what follows it. Half of 2 is 1. Half of 1 is 1/2. Half of 1/2 is 1/4. Half of 1/4 is 1/8. So it goes there and it goes there as far as you want. Okay. And you should know that. If I was to add, I'm probably not going to put it on as a problem. It's something you're probably going to need to do at least part of one problem. Okay. The whole halfway thing, we've kind of emphasized that through the course. With the construction of the graphs, everything is a halfway. Okay. Halfway between something and something else, it's already there. Make sure my powers of 2 are divisible. Okay. So I choose 64. I try to locate one of these values at a reasonable point, whatever the scale of the graph is, and then I start cutting them in half. Half of 64 is 32. And that's halfway from here to here. I put it a little too far to the left. You might do that too, but don't put it over here. Okay. I can tolerate a little bit of error as long as it looks like you know what you're doing. Okay. And then we cut that in half and get x equals 16. Now here, halfway between 32 and 64 would be 48. And so forth. So now we've got a scale for the x's. And of course, we can do negative values of x. If I have 32 here, then negative 32 would be about here. X equals negative 16 would be about here. Now the question, and the reason I use a random graph is so you won't be tempted to use a calculator to get your answers. We could also have a y scale. Okay, so let's say I tell you that a little ways above the highest point, we have y equals 8. Then we go halfway down to the x-axis, and y is half of 8, which is 4. And halfway from there to the x-axis, y equals 2. Halfway from there to the x-axis, y equals 1. Okay, now we've got a perfectly good scale. Then I ask to estimate the coordinates of every point where y equals, let's say y equals 6. Okay, that means we sketch the line where we think y is 6. Now I put it too low. It should be halfway between 4 and 8. Okay, so I'm going to say, I'm just going to fudge and say, okay, y equals 5.5. Still not a great estimate, still not a great place for the line. But if I ask you to look at, back up a second, we're going to call this function f of x. Now I want to solve f of x equals 5.5. This is how you begin to answer that question. Okay. Y equals f of x and make the line y equals 5.5. Gonna have to estimate, but that's okay. Now I'm going to say estimate corresponding x values. If I wanted to say it more specifically, I'd say estimate the x value at every point where this y equals 5.5 line intersects the graph. I didn't want to write that much, didn't want to take that much time. So we got this point, got this point, got this point, we got this point. What do? We draw a vertical line through each one. Well, that's pretty much what I said was x equals negative 32. Draw a vertical line here. Draw a vertical line here. Draw a vertical line here. And estimate x. I'm going to say yeah, it's about negative 31. It's a little bit to the right of negative 32. This between x equals 0 and 16, so I'm going to estimate x equals 7. It's a little to the left of the center. This is about halfway between 32 and 48, so I'm not going to split hairs. I'm just going to say that x is about 40 here. And over here, it looks like if x is 70 here and 64 here, I'm going to say it looks like maybe 75. So I got negative 31, 7, 40, 75. Okay. And then estimate f of 54. What do you estimate f of 54? You make a vertical line at x equals 54. Now, here's 48. Here's 64. Halfway between 48 and 64 would be 56. We're looking for 54. So I'm going to say that x equals 54. It's going to be a little closer to 48 than it is to 64. So still, okay, that's x equals 48. What's the value? Well, it just turns out, just coincidentally, because I didn't plan it that way, but this seems to be just right at about the peak. And we can sketch a line here and estimate y. If it's 8 here and 4 here, 6 in the middle, looks like it's about y equals 7. So the corresponding y is about y equals 7. Now we're not done with this graph. There's a really important characteristic. There are important characteristics of the graph that I'm not going to detail here. Well, I'll write down the answers. I'm abbreviating. The official words are intervals of increasing behavior. Well, it looks like the function is increasing all the way up to about this point. So it looks to me like it's increasing about x equals, well, let's see, what's the first x value I see in this graph? Now, it might be going to negative infinity, but I'm going to say for this graph, it's about x equals negative 50, negative 15. Okay, so that would correspond to, we'll make that interval of increasing behavior yellow. Stops increasing right about here where it hits the peak. Okay. And then it increases from about here to here. So x equals negative 50 to negative 15. And then x equals what here? Starts increasing here. That looks like about x equals 24. Halfway between 16 and 32. And it looks like it stops increasing right here at x equals and why did I write x equals 48 there? Okay, I've got to go back and say, I said it's halfway between 48 and 64. So, and I said that's about 54. Because halfway between would be 56. And then I went and wrote x equals 48, which was really misleading. X equals 54 at that point. And it looks like that's where it stops increasing. So x goes from 24 to 54, and it's increasing. Okay. Now, one other thing. It's not actually increasing when x is equal to negative 50. That's where it starts increasing. At x equals 50, the thing is level. So I should have used open parentheses. So again, x equals left parenthesis negative 50, comma negative 15, right parenthesis. Similarly on the interval from 24 to 54. What's the average rate of change on the interval? And I use a closed interval from 24 to 54. Now, it's really the average rate of change of y with respect to x, and that's the way it'll be stated if it appears in the final. Okay. I should have another color here somewhere, but I don't think I do. Okay. I've just sketched the line segment corresponding to the line segment between the points negative 24 and whatever the y value is, and 54. Okay, so there's the graph on the interval 24 to 54. Here's a straight line, and that's the hypotenuse of your fundamental triangle, which has a rise here and a run here. Then you want to estimate the rise. Okay, well, x is a little bigger than 4 here. It's about 7 here. So from 4 up to 7, I'll say x equals about 5 here. Okay, I'm going to take this triangle and I'm going to redraw it down here so we can label it a little better because it's getting kind of fluttered up there on the graph. This triangle is the same as this triangle up here. I'm going to say rise. I'm going to say it's approximately 7. Minus 4.5, which equals 2.5. Remember, when you draw a fundamental triangle, you start at the leftmost point, use an arrow for your vertical line, whether it's up or down. Use an arrow for your horizontal line. And your horizontal line moves, in this case, from 24 to 54. So the run, nice to have chalk that works. Run is about 54 minus 24, which is 30. Slope is rise over run, which is 2.5 over 30, which equals 1/12. Which is approximately 0.08. Refresh yourself on how to label these. I do want to see them completely labeled. You're going to lose points if they aren't. If they're generally right, they're kind of okay. It's probably worth 6 or 7 out of 10 points, okay? Depending on and maybe more, depending on what's missing. But I don't want any of this stuff to be missing if you want the 10 points. So try to get that straight. Okay? Now, this is all stuff right here, this kind of problem. You can expect a problem with this. Matter of fact, I'll guarantee it. Okay? And if I'm lying, I'll just give you another 10 points, average another 10 points into your grade. Okay? I'm not lying. I totally intend, but got a lot of off-campus issues to deal with. So it interferes with my sleep. Who knows what's going to happen? Okay? We'll get through it. There's stuff going on. Okay. And I do apologize for that. End of the semester is a terrible time, but I have no control over it. All right. Now, those are really foundational things. I'm not talking about linear functions because that should be straightforward. Okay, just be sure you review it because I'll put some linear functions on there. You should be able to, well, okay. I'll just write a couple of notes about what you really want to be sure you can do. Give them 2 points or give a point of slope. Okay, review that. Make sure you refresh yourself. Everybody has known how to do that. So just be sure you're up on it. And apply. Okay. And that means if a house is worth $200,000 in 2024, okay, or was worth in 2024, and it's worth $450,000 in 2030, then if you assume a linear model, what's it worth right now? Okay. What's it worth in 2040? Okay. You have problems of that nature. There's a whole section of problems, and they just require that you put 2 points on a graph and find the slope, or put 1 point on a graph and give them the rate of change. I could ask you for rate of change. Find the rate of change. Find the equation given a point and rate of change and use it. Okay. Review the section and applications of linear functions. And what I told you is basically start with a graph, the 2 points on the graph. If you have the information to give you 2 points, if you just have 1 point and a rate of change, well, indicate the rate of change. Rate of change is the slope. Okay. And it is average rate of change of y with respect to x. So expect to see that terminology with any problem. Okay. Now, power functions. Even powers look like this. Odd powers look like this. The higher the power, the flatter the graph is in the middle. But they both get flat at the vertex. I didn't quite draw that right. It should be getting flat right there. It's the origin, but you get the idea. You might need to review that. Okay. So this is like x to the fourth, x to the sixth, x to the eighth, etc. That's even powers. Odd powers are like this, e.g. x cubed, x to the fifth, x to the seventh, etc. Polynomial. Some number a times x minus c1 to the p1 times x minus z2 to the p2 times x minus z sum n the p sub n, and actually I probably don't want to use n there. I'll use m. I'm going to use n when we expand it. Okay. Zeros at x equals 0, z1. I'm going to give myself a little over. X equals z1 multiplicity p1 like the power function x is a p1. In other words, whatever the power is here, it's going to go through 0 or touch 0 at that point. If p1 is an even number, then it's like an even power. X squared, x to the fourth, x to the sixth, x to the eighth. Okay. So don't let the notation distract you. Z1 is just some x value where the thing's going to hit the x-axis. So for constructing a graph, we say, okay, here's x equals z1. It's going to act like a power function. make a little note that it's power P1, whatever it is. If Z1's negative 12 and the power is 5, then it's going to get this like a fifth power. Okay. And then we got x equals C2 power P2. For example, if this is x equals negative 12, and this is x equals 6, and the power P1 is power 3, power P2, for example, power 2. Okay. Then, if it's power 3, that's an odd power. It's going to look like this when it goes through 0. Now, when I say it's going to look like this, I'm going to draw it very lightly. Or it could be upside down. So it's either right side up like this or upside down. We don't know which until we do the rest. Okay. And if it's power 2, let me draw these two little curves in opposing colors. It's either going to be the yellow graph or the white graph. It's power 2. It's either going to be a parabola opening upward or a parabola opening downward. Whether it opens upward or downward, whether it's inverted or not from the toolkit shape, just depends on what A is and what any other zeros might be. Okay. Then I'm not going to require that you figure that out or represent that, except maybe as an enhanced problem that would be worth a little extra credit. So I've talked about it, gone over it. So if you happen to pick up on that, it might be worth your time. But pick up on everything else before you spend too much time on that. Okay, but this is going to be important. So you agree? Well, if you expand it, you're going to get different powers of x. You know that if you've expanded these. You might get x to the 4th plus 8x cubed plus 5x squared minus 3x plus 12. Okay? Might get just about anything. Your x to the n term is going to be x to the p1. Because if you expand this, you're going to get an x to the p1, right? If this is the cube of x minus some number, then you're going to get x cubed plus some. Okay? So what you get, and then from this one, you would get a, if it is like x to the 5th, you get an x to the 5th here, right? I mean, sorry, P2 is 5. When you expand this, you get x to the 5th. When you expand each one, you get x to whatever that power is. And you get a bunch of other stuff you're not going to be able to analyze. Okay. In order to analyze the thing, you got to have the factored form. So I'm going to write it like this. X to the n is x to each of these powers multiplied all together. And that means since multiplying powers, multiplying x to one power by x to another power, you're going to add those powers. That's one of the rules of exponents, and you got to know those rules. That means you're going to have power P1 plus P2 plus Pm. So n is just the sum of all these multiplicities. Then the zoomed out form you've got y equals x to the n, which is going to look maybe if n happens to be an even number, it's going to look something like this. And the wiggles that you get because of this stuff are going to look like this. They're just going to be confined close to the origin. So if you do the complete graph, if this is the leftmost power, power furthest to the left, that means the graph is going to have to take off steeply right after you're here. Okay. So it means it's going to be very steep. So that means your end behaviors are going to be the end behaviors of this zoomed out function, which could look like this or could look like this, depending on whether adding all these powers gives you an even or an odd, or whether expanding gives you an even or an odd. So it's going to do this and it's going to do this, which means that if I try to draw the graph, if these are the only two powers I have, then the graph is going to have to come down very steeply like so, come down here and flatten out and go down. And then okay, I should have looked at my example before I said this. This is even power. And without a whole lot of explanation, this is odd power. What I have here is power 3 and power 2. If these are the only two powers, that means I'm going to use the odd power for the end behavior is like this. So we're going to come here, we're going to turn around, and we're going to have to be upside down here, and then we just go on down like this. Okay, well, that's an overview. It should remind you of what you need to do. So be able to draw these things. Okay. Rational functions have vertical asymptotes. Okay. And I hate to leave it out, but this semester, having been interrupted a number of times, I'm probably not going to include a rational function. If I do, it'll be a very simple one. So you want to review rational functions. But I want to finish talking about other things here. Okay, so I'm not going to talk about rational functions except to tell you to review rational functions, which have graphs that can look like power functions sometimes. And like rational functions with vertical asymptotes and stuff, okay? So you have x-intercepts. This means that you have, if that's like x equals 5, -5, you would have x minus -5 squared. So the thing would act like a parabola there. Here, it could just be plain old x minus 1, okay, or x plus 1. X minus -5, that'd be an x plus 5 squared, or an x plus 1 squared would give you 0 here. That would act like this, and so forth. All those characteristics. You also have a vertical asymptote, which means your denominator is 0 at whatever value of x you get here. So review that. But if you don't think you understand it well, don't spend the majority of your review time on it. If you've got 10 hours of review time, don't spend more than 15 minutes on it. Not going to be that important on this part. Okay. I'll get back at you with something else. And when I drew my odd power here, it was not visible. But here's the way an odd power would behave with its exponents. And as I observed, if you got an even power 3 here, and an odd power 3 here, even power 2 here, that gives you odd power 5, which means things don't act like this. That was the basis they used for getting the end behavior here and here. Okay. Then we move into exponential functions. Again, we saw at the beginning that these are like y equals b to the x, or ab to the x, okay? Or a e to the kx, or a times 2 to the kx. So generally it's y like equals a b to the t plus k. What the a does is vertically stretches it. And what k does is it raises the asymptote. So I'm going to say we typically use k to the number here in front of t. And I'm going to use a c because we also use k with a vertical shift. That's a little bit of an unfortunate coincidence of notation. Okay. You look at these two forms, and AE times 2 to the CT plus K is treated in the same manner. First thing, the graph. I want to draw a couple of graphs here just to cover some of the possibilities. Okay, first of all, the most fundamental graph we draw looks like this. K equals 0. There's no vertical shift. the asymptote is at the x-axis. And I'm not going to mention, oh, well, yeah. All kinds of things I can do with these graphs. If, for example, I have a graph that does this, and it's exponential, this is the exponential shape, just turned upside down. It's actually turned around and reflected. I don't want to go into that much detail right here. A would be negative. The asymptote would be at y equals k. And C would also be negative. If you take this and flip it over the x-axis, the asymptote is on the left. Okay? If you make C negative, that flips things around the y-axis as you learn in the first chapter. And it ends up looking like this. Okay? So let's just kind of overview what they look like. Let's look at how to analyze them. Y equals f of t equals ab to the t. Let's say we want to solve f of t equals q. I'm just going to do it with symbols because it's going to be the same as it would be with numbers. Okay, so what we have is ab to the t equals q. We remember that b to the a equals c is equivalent to log base b of c equals a. Now there's a little bit of a problem here. I've used a for the coefficient of b to the t, but I've also used a as an exponent here. Okay? So this is the rule. And sometimes, as a coincidence, a or b, even b, but hopefully not, or c, could be part of your equation where it doesn't really mean a, b, or c. Now that can be a little confusing, but what I mean by that is if this occurs, first of all, you put this in the form. This is just saying b to some power equals c. Okay? That's what we want here. We want b to some power equals some other number. B to some power equals something. So we divide both sides by a. You get ab to the t over a equals q over a. B to the t equals q over a. Now in this form, somewhat confusingly, a is the power. A in this form is t. C in this form is whatever's to the right of the equal sign. That tells us then that the log B of Q over A equals T. There's our solution. Now, to make that a little less confusing with the A's, I'm going to go Greek on you here. I'm going to change all my A's to Greek alphas. So now we don't have an A over here to confuse with the A over here. So you look at it this way. So in any case, this is a simple equation to solve, but you have to know you got to divide by whatever's in front of B to the T, because this form doesn't address having something in front of B. Okay? That's the one pitfall that I see people fall into. And so to solve exponential equations, you got to know this. Okay? So you really want to focus on that. Okay? You want to be able to find a half-life or doubling time. So if you have the form AB to the T, you solve AB to the T equals 1/2 A. Why? Because if T equals 0, AB to the T equals A. Any number to the 0 power is 1. Okay? And you want to know the T that changes your value from A when T equals 0 to 1/2 A. Okay? Now, to be pretty explicit about it, I'm going to use T sub D. T sub D is your doubling time, or it could be your, well, it could, so yeah. If T, let me restate what I just did a minute ago. I'm thinking doubling time. I'm thinking half-life, and I'm talking doubling time. If it's a doubling time, you should double A. You should double whatever number is in front of B. If it's half-life, you solve an equation like this. Example, and again, half-life of y equals A times 0.7 raised to the T power. Okay. of 80 times 0.7 to the t equals half of 80. That gives you 80.7 to the t equals 40. Divide both sides by 80. And you get 0.7 to the t equals 1/2. So t equals what? Well, this is in the form b to the a equals c. So t is going to be log base b, which would be log 0.7 of 1/2, and you just punch that into your calculator, and you will have a calculator. You took the midterm, you know how that works. Got to use their calculator, and it doesn't do all the fancy stuff. It does quite a bit, so you find it useful. Okay, well, that's just an example. So review, half-life and doubling time, that's important stuff. And go back to what I showed you originally, first sketch I drew. Make sure you understand that half-lives, you just do the standard sketch of an exponential and then label the t-axis or x-axis by half-lives. You get a graph that's going to give you a pretty good indication of how the function works. Okay? Okay, then that's the most important stuff, and I'm not able to cover everything. We covered exponential functions fairly recently, and the homework that I've gotten has looked pretty good on exponential functions, okay? Polynomials hasn't been that bad, but make sure you review it because it's been a little while. Exponentials is fresh. And then systems of equations and matrices, well, we've been over that pretty thoroughly, okay? Doesn't mean that everybody's really good at it, okay? So you're going to have to review it, but let me give you a quick overview. And I'm just going to do a system of two equations and two unknowns. You should understand that that translates right over to three equations, three unknowns. You've got more numbers to work with. Procedures are very much the same. So let's say I've got 4x minus 3y equals 7, 5x plus 8y. I don't want to get into that. So I'm going to say 6x plus 8y equals -2. Okay. This is equation 1. This is equation 2. I can do -3 times equation 1. You probably can't read that. But if I multiply this equation 1 by 3, I get -12x plus 9y equals -21. If I do 2 times the second equation, I get 12x plus 16y equals -12. That's right. Something's wrong with my numbers. Shouldn't be, though. Okay, well, let's see what happens. So I can't be right. 2 times -2 is 4. So I should have -4 here. Okay, sorry. I add these up, I get 25y equals -25. Solve that. I'd write out the step. You get y equals 1. Plug y equals 1 back into the first equation. And you get 4x minus 3 times -1 equals 7. 4x plus 3 equals 7. 4x equals 4x equals 1. Now, all those steps are really straightforward. You should be able to do that, maybe not as quickly as I did, but probably more accurately. Okay. Augmented matrix. And so there's an augmented matrix. A lot of times you want to have a 1 here, but you don't need to really get a 1 here until the last step. If it's more convenient to have 4 here, since if you divide, okay, if you want to get a 1 here, you divide everything by 4 and you get some fractions, -3/4, 7/4, and all that stuff. You can avoid that by just leaving equation 1 for row 1 the way it is. That row 2 would then be in the next step would be three times row 1 minus 2 times row 2. Now we've only got a couple of minutes, so I'm not going to write it out, but then you write that calculation off someplace else, not in the column. What you're going to get is you're going to have 4, -3, 7, and you're going to have 0, and you're going to have 25, and -25. Row 1 hasn't yet been messed with. Now what I'm going to do is I might just take row 1 and divide it by 4, giving 4, -7/4. It's -3/4. That should have been a 3. And 7/4. 0, 1, -1, because what we're going to do is divide row 2 by 25. Dividing this and this by 25 gives me 1, -1. And that's 2 equations that I can easily solve. As a matter of fact, well, it's going to give me the 2 equations, 4x, sorry, x. If I divide by 4, I'm sorry, I had a 4 here, could have been a 1. I get x minus 3/4 y equals 7/4, and y equals -1. Well, I just plug the -1 in here, and I get negative, well, 3/4 of -1 is -3/4. Negative that is plus 3/4. Add 3/4 to both sides, we get x equals 1. So these equations are easy to solve by back substitution. And finally, I don't have any room to do it. I'm going to break down and maybe see if I can. It's line 4 to use. Okay. And very, very quickly. Okay, again, the same equation. We'll write it out, 4x minus 3y equals 7. 6x plus 8y equals -2. Can be written as a matrix equation, 4, 3, 6, 8 multiplied by x, y equals 7, -2. And if you understand matrix multiplication, multiply the 4, 3 row by the xy column, you'll have 4 times x plus 3 times, and it should be minus 3 times y, which matches your first equation, right? And 6 times x plus 8 times y has to equal -2. There's your second equation. So that should be very easy, but make sure you review it because there's a very good chance it'll show up. Okay. Okay. I've enjoyed working with you guys. I wish more people had stayed with the course. I just have a feeling when people realize they can't just use AI to pass the course, they just disappear. It's happening in all our pre-calculus courses. And we've got to do something to address that and figure that out over the summer and change things a little bit. But I'm glad y'all stuck with it. Review real well. Enjoyed working with every one of you. And hope to see you in the future. Okay. Have a good one. Have a great summer. Gee, I hope I was recording all that.